Hi, Miriam. All right, folks, it's 10 o'clock. I guess I'm just doing it for the people who are watching this on the record. So, because I don't think there's anybody else here. I did have one person, but they seem to have disappeared. All right, well, what I'll do is I'll go through this test first, and then I'll try and relate it back to what we're doing in test 4 here. The stuff in test 4 I find is not incredibly challenging. I do want to remind you, though, that we do have a situation here where we have the test, which is worth 70%. Then we've got the essays, which is going to be worth 20%. And then you've got the units quiz, which is worth 10%. All right, so let's go take a look at what's in the test. Hi, Miriam. So we've got the first one. We've got to calculate the time required for 80% of a sample of something that's radioactive to decay, and I will go through some examples of these on the test in a second. The other thing we talk about here is modes of decay. This becomes a whole lot easier, I think, when you can actually use notes. So I would recommend watching the video about this that goes through the different modes of decay. You'll find that they're not incredibly difficult to understand. Hi, Rebecca.
Hello.
So we've got an atom. All right, excellent. Okay. The other thing we've got here is this mass defect type calculation that allows us to determine the amount of energy released using the Einstein formula E equals mc squared. And
Nice.
then we've got our concentration and colligative property type problems here, which some of you will be familiar with because, well, I know I went through them at the end of my Chem 1 class. So you've probably seen this before, or some of you have at least. And then the last thing here is coordination chemistry. And the way I've got this set up in the test, it's kind of not too difficult. I'm pretty much hoping to get through a lot of this stuff today. Next week, I have cancelled the Zoom session because I'm running my lab final during that time, and I don't really feel like we need to have one anyway for test 4. My advice here for test 4, get the essays and the units quiz done early. There's no real reason to sit around and wait to do those. You will need the time at the end, I think, to make sure that you get everything done that you need to get done here. So we've got this here. All right, so test it was going to be due next Thursday. I think what some of you might do is be inclined just to kind of wait until Wednesday to start studying. And, you know, I'm actually, you'd be surprised. I'm going to say, well, you're probably okay doing that because this is actually not that bad a test. As long as you've got the essays and the units test done, I think you could probably get away with just spending Wednesday or even just for Thursday on this material and still get away with doing pretty well on this test. Especially with having a page of notes. I just don't see how it could be any easier, to be honest. All right, let's talk about, well, I guess I'll just move straight on to the test here. We'll just go through test questions. Yes, a student made a point to me today about whether we needed a periodic chart or not on test 4. I said, no, we don't need one of those. And, you know, they're all pretty much fake elements. But there is one question that does require a periodic table. So I have added one. You won't need one for the test. You see, there it is there. And I want to remind you that anytime you've got a periodic table like this, you can always enlarge it by doing Command plus or Control plus, depending upon what computer operating system you're using. And then you can do Control or Command minus in order to shrink it. All right, let's take a look. Radioactivity. I do have a couple of equations here. I think you should make sure that you understand that they're there. You don't have to do anything else with them. You don't have to memorize any of them. So that's what you'll be using on the first question here. Calculating the time required for a sample of this. Now, this is why I didn't think we would need a periodic table, is because I'm just going to be pretty much using these fake elements here in order to get the job done. So well, that's the thing. I don't really want to go actually spend any time doing these unless anybody's got anything specific. Does anybody have anything specific about questions 1 or 2? All right.
No, not yet.
No, I'm going to focus more on the stuff that's hard. You know, this stuff is relatively easy, and you won't really have a hard time with it if you watch the videos associated with it. So I'm going to not do anything with questions 1 and 2 here today. Now the other questions 3 through 12, all have to do with specific kinds of radioactive decay. I will do a couple of these just to kind of get the ball rolling, and just to make sure that you understand the concepts behind what we're doing. And you'll see it is fairly easy here. So we've got an element that has an atomic number of 52 and a mass number of 101. So first of all, when you're expressing this kind of situation, just use an element X, just because I haven't said anything here. You put the atomic number down here, and you put the atomic mass up here, atomic mass or mass number. And of course, what you are already aware of is that the atomic number here is equal to the number of protons. And this mass number is going to be the number of protons plus the number of neutrons. That way we can easily determine how many protons there are, how many neutrons there are, because we know how many protons. Does anybody have any questions so far? Now, if we're going to talk about alpha decay, then we have to be aware. Actually, I shouldn't probably call that X. I should probably call it something else, because I want to use something else. I want to use X for something else here. I'll use Q as my element here, because I want to do this X, Y, and Z here, plus, and then alpha decay, I'd have to know that it's the release of a helium nucleus. And if I do that, then I can easily determine then what this element here, this mystery element, or what I like to call the element of surprise, is going to be 50. And then up here, 101, that would be 97. And then if you wanted to, I mean, we can just leave it as X, but we could actually figure out what X is by hunting it down on the periodic table and just looking for something that has that mass number. There it is, 10 would be the answer here. So X, if you wanted to, you could make it equal to 10.
Wait, the atomic number, that's the amount of protons and neutrons, right?
No. The atomic number is just the protons.
Yeah, okay.
Okay, the mass number, the one on top, that's the protons and neutrons. That's how you can figure out how many neutrons there are, because you can always subtract out the protons from that to get to neutrons, which we'll be doing later. But I guess the whole point of me doing this was just to show you how easy it is just to do a little bit of simple algebra in order to figure out what this mystery element is. So that's alpha decay right there. And if we had beta decay, what I'm calling beta minus decay, that would be Q gives, again, X, Y, Z plus an electron. Now, an electron has no mass, so the mass number is 0. And because it has a -1 charge, which is equal in size to the positive charge that we see in protons, just with a negative value, then we say that it has effectively an atomic number of -1. So that's what an electron is. And this is beta minus decay. That's loss of an electron right there. The other ones we talk about are going to be beta plus decay, which is positron decay. Now, positrons have the same mass as an electron, none, and the exact opposite charge. This is an example of antimatter. It's an antiparticle of the electron. Now, anybody who's a fan of science fiction knows what happens when you take matter and antimatter and you put them together. They annihilate each other and form energy. So this is an example of antimatter. You didn't think antimatter existed. This is an example of it. No crap. It's true. Sorry, I didn't mean to say that. Can I go back and edit that? Just kidding. I'm just joking.
We need a little chemistry humor.
But maybe a little bit.
Yeah.
All right. What do we yes.
The E stands for electron, correct?
That's right. Yes, it does.
And the 0, well, it's the same format. So there's no mass to it.
Well, it's very small mass. In fact, I'd say negligible compared to the mass of, say, a proton. An electron actually weighs 0.00055, whereas a proton weighs 1. So that gives you an example of what we're talking about here.
You said 3 zeros?
Yes, 3 zeros.
55.
That's right. 0.00055. Whereas a proton or a neutron weigh both the same. They weigh about 1. I'm talking about atomic mass units here, AMU. But that's just a unit that allows us to compare the mass of things that are in the nucleus. But effectively it's 0. And for our concerns, let's just call it 0 for the electron. Okay.
All right. And you said the beta plus is called positron.
That's right. It's called a positron. It's like a positive electron, right? I think it's a great name. Yeah.
It's catchy.
It is catchy. It is catchy. I like it. All right. What else have we got here? We've got the alpha decay. We've got the beta minus decay. We've got beta plus decay. We've also got K electron capture, which is, I don't really want to go into where that terminology comes from. I do in the video. It's kind of interesting. At least I find it interesting. And what happens with K electron capture is that the element itself takes one of its electrons from its inner shell, which used to be called the K shell, by the way.
Is that wait? Are you referring that like from the valence electron shells or whatever? Or?
Yeah. But it's from the very inner row of electrons, not the valence electrons, of course. Yeah, you know how there's 2 electrons in the inner shell?
Yeah.
Right. It's actually, the nucleus is actually interacting with one of those electrons, which changes it into a whole new element. So that's K electron capture. And the last one is gamma decay. Which don't change nothing. All it does is release a very high energy photon. And that photon is a gamma ray. And the rest of it stays the same. So the nucleus is unchanged as far as the number of protons and neutrons go. But overall, it's lower in energy because it's lost a photon, a high energy photon.
So,
go on.
the gamma ray, the photon, that's just a light right there.
Yes, exactly, but a very high energy light. You know,
So that'd be considered radiation?
absolutely it would. Absolutely would. If I had a choice, Adam, if I had a choice, and somebody came up to me and said, look, I'm going to give you three portions of radiation. Which one do you want? I tell you what, I wouldn't take gamma. I wouldn't take gamma, and I wouldn't take beta. I'd take alpha if it was me. You know, an alpha particle is, as I've got up here, it's a helium nucleus. It's a very heavy kind of thing to be released by an atom. But the thing is that you can stop an alpha particle with a piece of paper. But if you're dealing with an electron like this, a beta radiation, you need
something to absorb that electron.
Yeah, 2 inches of lead. 2 inches of lead required to absorb that. And a gamma ray, 6 feet. 6 feet of lead required to absorb gamma rays. So when you talk about the most dangerous kinds of radiation, we're talking about gamma rays and beta particles. And these are the things that cause radiation sickness because they interact with DNA by ripping electrons off DNA and causing mutations in DNA, which then leads to all sorts of nastiness down the line.
And this just reminds me of Chernobyl.
Mm-hmm. Yeah, that's right. Yeah, I can really recommend that. If anybody's not watched that series, you should watch it.
It's a good one.
It is excellent. All right, let's take a look at question 13. Again, not particularly difficult. None of this is really very difficult, I don't think. I know I've said that in the past about a bunch of other things, and you've said, "What, Dr. Musgrave, you're crazy." But this time, I think I'm on track.
The gamma ray capture. What was that again?
6 feet of lead.
No, like what you wrote down.
Oh,
sorry.
Sorry. Well, no, it doesn't change anything. Whoops.
It's like a upside down ribbon.
Well, it's a gamma. It's the Greek letter gamma.
Ah.
Yeah, it does look like an upside down ribbon, though. I agree with you.
Thank you.
So 13, you know, this isn't difficult. The only wrinkle here is that just understanding this 3-1N business here. Now, the N is a neutron. Now, think about what a neutron is. Word neutron means neutral, right?
Yeah.
No charge, right? So the atomic number is essentially 0. You'll notice here that we often don't include the atomic number because we already know what the atomic number is. We can either get it off the periodic table or we know from the symbol what it is. So so for N, that's going to be 0 and 1. So if you've got 3 of them, then that really is effectively 3 of these neutrons. I won't include the 0 here, so I didn't put it there in the question either. So it's just like that. So it's a neutron plus a neutron plus a neutron. So figuring out that value of X as to what the mass number would be is not particularly difficult. It would be like this. 211 plus 22 equals 80 plus our X plus 3. And then you can just solve for X. We could technically do the same thing with atomic numbers as well. But in this question, you're not asked about that. You're only being asked about the mass number that we're looking for there. Does anybody have any questions? You look concerned. Adam, are you all right?
I'm still waking up.
Oh, okay. Fair enough.
Yeah, I got distracted by my phone because it was super loud.
Oh, okay.
Sorry.
Does anybody have any questions about 13?
No, it seems pretty straightforward.
Yeah, it's not too bad. One could even argue, I'd like to say this just straight out here. I think this could even be considered just a little bit fun. Dare I say it? Fun?
I hear the fun in your voice.
All right. Let's take it.
I
Go on.
actually have one concern.
Okay.
The three ends, whenever you refer the neutrons with no mass, right? Or no
Oh,
atomic number,
no charge.
no charge.
Yeah. Remember, the atomic number is essentially the charge, right?
Yeah.
So if you've got 4 protons in a nucleus, that's a charge of +4. That's why the atomic number is 4. If you've got an electron, the charge is -1. That's why the atomic number for an electron is -1.
Okay.
So think of it that way. And neutrons, since they have no charge, are just going to be 0 because they're neutral.
Okay. And on that last equation right there, do we just do algebra to find x?
Yes, absolutely.
And whenever we find x, that's just the atomic number, or
No, in this case, it's the mass number. If you look at the initial question, these are all mass numbers up here.
Okay.
But there's nothing to stop us doing the same thing for an atomic number, Adam. We could do the same thing if we knew what the atomic numbers for A, B, and C were. We could figure out an atomic number for X. But that's not required here. We're only looking at the mass numbers.
Yeah. All right. It's just set up for that, for the mass numbers. Yep.
Yep. Look at the question. See, the mass number of X is, right?
Yeah.
All right. Now, I do want to focus on 14 and 15 because these are a little bit difficult. This is the one for which, the student alerted me, said, well, don't we need a periodic table for this? I wrote back to him and said, no, why would you need a periodic table for this? And it turns out you actually do. So I did apologize to that student. That was kind of funny, actually. I was thinking, oh, you know what? He's right. We do need a periodic table. All right. Well, fair enough. Okay. Well, let's see how we deal with this. So we've got an element that has an atomic number of 41 and a mass number of 110. Using your determination as to whether it's proton or neutron rich, what's the atomic number of the element it becomes after radioactive decay? Ooh, interesting. So this goes down to the depths of why things decay radioactively in the first place. So let's go take a look at the periodic table here. So let me write that down. It's X41, 110. So that's the element we're dealing with here. And of course, we can actually go to the periodic table and we can actually identify that puppy. 41, there he is, NB. So it's NB is what we're dealing with for X. Now, if you take a close look, and I go through this in one of the videos, it's actually kind of interesting. I do recommend looking at that video. Come on, there we go. I do recommend looking at that video that goes through this. But if you look at the protons and then you look at the mass numbers that are on here, you'll see, first of all, the mass numbers are not whole numbers. And the reason for that is because all of these elements are mixtures of what we call isotopes. Isotopes have the same atomic number, but different mass numbers, which means different numbers of neutrons. So same protons, different neutrons. This number here is actually all of the isotopes averaged for natural abundance. So the more abundant a specific isotope is, the closer this will be to that mass. So let me give you an example. Look over here at chlorine, 35.4527. If you look at chlorine, you'll see that 2/3 of chlorine, around about 2/3, I'm being a little bit estimating here, but about 2/3 of chlorine is chlorine 35, which means that's chlorine with 18 neutrons. The other third is chlorine 37, which is 20 neutrons. All right, so it's the same deal, just same atomic number, just a different number of neutrons. And you can see here that the total mass is 35.4527, which takes into account that there's more chlorine 35 than there is chlorine 37. But you can see it's not that close to 35, indicating there are many isotopes that have higher mass than that.
Wait, so radioactive decay just determines like other parts of what elements are like capable of doing?
Oh, we'll get to that in a second. But those isotopes of chlorine are actually stable, but not all isotopes are stable, right? But I'm going to get to that in a second, Adam. I'm just trying to explain why these are not whole numbers. That's all. That's my only aim right now. Okay.
Is it like a mean average kind of thing?
Yeah, it is. Yeah, it's an average based on how much there is of each isotope. Now, some of these have multiple stable isotopes. Tin, for example, has 10 stable isotopes. 10. And a whole bunch of unstable isotopes as well to go along with it. But the argument I was going to make here, if you look at the protons and you look at the mass numbers, you'll see that the mass numbers up to about element 20, and this is important, up to about element 20, you'll notice that the mass number is about double. See, it goes 20 and it goes 40, which tells you you've got 20 protons and you'd also have 20 neutrons. So the number of protons and number of neutrons in the nucleus are pretty much the same for small nuclei, for small elements. But look what happens as we go down here. Well, I'll just pull something random here. Let's look at something easy. We'll look at fermium here, right? It has an atomic number of 100. That means it has 100 protons. But its mass number is 257, which means that there's 157 neutrons. So there's a whole lot more neutrons than there are protons in this puppy. A whole lot more. Now, why is that? Well, I would posit that part of the reason for that is that if you've got a small number of protons in a nucleus, then, you know, it can somehow deal with those charge repulsions that you'd expect between positive things like protons. But if you've shoved too many protons, like 100 protons into such a small area or volume, then what's going to happen is, you know, at some point you're going to have so many protons in the nucleus it's just going to want to fall apart or fly apart. So the only way that you can mitigate that charge is by putting in neutrons in order to balance that out. But at some point, it won't matter how many neutrons you have, there'll be too many protons in the nucleus and it'll just fall apart on its own anyway. That's radioactive decay. And what it is, it's an excess of protons for the number of neutrons you have, or it's an excess of neutrons as well, one could argue, that would cause it to fall apart. So that's what we're finding here. Again, look at the video. The video is important here if you truly want to understand what I just talked about.
Right. Well, I mean, from what you were just saying, it was just like, if we just look at calcium, I mean, the atomic number is 20. So there would be 20 neutrons.
Yes, that's right.
So it would just be balanced like the entire time and stay almost the same and like decay by like 700th and 8,000th, right?
No, it just wouldn't decay, right? I mean, right. It'd be stable. But let's say you have 50 or 60. Let's say you got a mass number of 60. That means you've got 60 neutrons. That would be too many neutrons. If you had 35 as the mass number, that would be too many protons. Right? It's stable. It's stable. Right. It's stable when it has 20 and 20.
Yeah.
How do we know that? Because if I'm telling you that the mass number is indicative of the number of the stable isotopes, then this gives an idea of the what the stable element would be. So a stable isotope will match the mass number here. So let's take a look at NB, and stable, if I'm going to look at stable NB, where is NB? There he is. Stable NB would be this.
92.
No, I'd say 93, we'll say.
Okay.
So stable NB is going to be 93 NB.
Right.
Right? Now, from that, we can do a little math. We know that NB is 41. So we know it has the number of protons is going to be 41. And the number of neutrons is going to be 52. All right, do you see how I got 52 there, Adam?
Yeah, I was looking at X for a sec. I was like, yeah.
Okay, no, we're just looking at stable NB for now, right?
Yeah, yeah.
Now, if we look at X, we know that the number of protons is still going to be 41, but the number of neutrons here is going to be
17.
Huh?
Yeah.
50.
Whoa, hold on. What's the weight of it, or the mass of it?
110, right?
What did I just write down? Oh my. Never mind.
So the number of neutrons there is going to be 69. So what I would argue there, I think successfully, would be that X has more neutrons than it should have, based on what it should be if it was stable. I would call this neutron rich.
So, whenever you call NB stable,
it's based.
What would necessarily be stable about it if there's more neutrons than protons?
Well, no, that's the whole thing. As elements get heavier, as you add more protons, you need more neutrons to mitigate the effect of the protons in the nucleus. Because the more protons you have, the more chance there is at some point it's just going to want to fly apart because you've got so many positive things in such a small area. Now, let me give you an idea of how small the nucleus is, Adam. This is really important. If you had a grain of rice, and you put it in the middle of a football stadium, that's how small the nucleus is in an atom. So think about that. So you've got all of these protons crammed into an infinitesimally small volume. Can't you imagine a situation where you put too many positives together, it's just going to want to fly apart? Right, so as we increase that number of protons, we need more neutrons relative to the protons in order to make that work. How many more? Well, we can look at the periodic table to kind of get an idea of that. So we've got our situation there. We know it's neutron rich. And we've got two modes of decay that we talked about earlier. We've got beta minus decay. And we've got beta plus decay. So if something is neutron rich, what it's going to want to do is try and get rid of those neutrons. And what it can do is it will turn neutrons into protons plus electrons. So that, if you think about what's a neutron, I should say. So
wait, you said beta negative?
Yeah.
Turn neutrons into proton plus beta negative.
Yeah, or an electron.
Ah, yeah.
Which is the same thing here. But think about what a neutron is really. It's really just the combination of a proton and electron that's kind of cancelled out, right?
Yeah.
Yeah,
So
that's all
I'll just
neutron
make it
is.
neutral.
Yeah. So that's what I'm saying, that anything that's neutron rich will tend to decay via this mode of radioactive decay, as beta decay, just like this.
Yeah.
Right? And that's how we know. That's how we can answer the question. So then we can just apply what we already did about beta minus decay and figure out what the element would be that we'd get from that mystery element that we talked about, this one that's 41 and 110. Let's take a look at the other example here. Unless somebody's got a question. Anybody got any questions? Okay. Let's take a look at the other example here where we've got 43 and 83. And then we can look at the periodic table. We can figure out what 43 is. 43 is Tc. And it has a, this would be Tc as well, of course.
What X will be?
Yeah. Because we know what the atomic number is, right? I get that off the periodic table. So 43 Tc and stable Tc is equal to, oh, sorry, I didn't mean to put the 43 up there. Let me erase that. Erase to 43 here, sorry. So Tc stable is equal to 43 and 98. So that would mean we'd need number of protons would be 43. The number of neutrons would be 55. And if we look at our example here, the number of protons is still 43, but the number of neutrons now is 40. So what that tells us is that it's neutron poor, but another way of saying it's neutron poor is saying that it's proton rich. All right, so that's proton rich, which means it's going to decay by this other mode of decay that we talked about earlier, which is positron decay.
That's if it's proton rich, right?
That's right. Because you can think about this, a proton will turn into a neutron plus a positron. And that's how it will get rid of its protons. And this is why anything decays. It's either to form more protons or get rid of extra neutrons. That's really it.
That's cool.
Yeah, I think it is. All right. Anybody have any questions? Okay. Now, the mass defect thing, it's pretty easy. I know, I'm still working on formatting this. For some reason, I can't seem to pad out these cells and make there's more space between them, but you can still see what we're going on about here.
Wait, so mass is atomic mass unit?
That's how this is measured, yeah.
Okay.
Now I do have a conversion for that up here, Adam. See, 1 AMU is this many kilograms. It's pretty tiny.
That's a small number.
Yeah, it's pretty tiny. Yeah. But, you know, the thing is atoms are small, right? So the things in those atoms don't weigh very much.
Right.
But, you know, the point can be still made that we can still work on these kinds of equations by looking at the mass numbers and the AMUs here. And what we can do is we can determine a mass defect. Now, the mass defect is going to be pretty easy to calculate. I'm not going to do it here, but the mass defect is it's going to be the sum of the mass of the products minus the sum of the mass of the reactants. And that's going to be a negative value. Right, so that's how I've worked this out. I've worked it out to be a negative value. The reason for that is
that's sigma m products.
Yeah, mass, just mass.
Oh yeah, yeah.
Right. So it's easy math. I mean, you know, it's really 4.1690 plus 5.1010 minus the sum of A and B. Right. So it's an easy thing to figure out this mass defect. Do you have any questions about that?
Not yet.
Okay. Now, the thing is that the mass defect is actually going to end up being converted into energy using our famous formula here, E equals mc squared.
Hey, nice.
And the mass there is in AMU, but the problem is that we need to do some conversions here. We need to get the mass into the mass into kilograms, and then multiply that by the speed of light, which is 2.998 times 10 to the 8th meters per second squared.
That's the C constant, right?
Yeah, that's right.
Hey.
Yeah. And then you do a conversion into gigajoules, which is 1 gigajoule is 1 times 10 to the 9th joules. And anyway, I'll leave that. I'll leave
that much.
What's that? That's a lot. Yeah.
That's a lot. Yeah.
Yeah.
That's a lot. That's a lot of energy.
It is that's why nuclear energy is so it's so attractive, is because you can have a small amount of material and still get a very large amount of energy from it.
It's like you can just power a lot.
Yeah.
Yeah.
Well, that's why people risk so much with nuclear fission and power from nuclear fission. You go back to Chernobyl, you can see what they'd risk in order to make that a reality. All right.
Oof.
Yeah. So anyway, I think you can probably work on this yourself. You can get look at the video for that. It's not difficult.
Said gigajoules is 1
No, it's
times
over
by 10 to the 9.
Yeah, it's over here. It's over here.
Oh, my bad. I got my Zoom covering it.
Yeah. Anyway, it's there.
Yeah, there we go.
Okay.
Dang, that's crazy.
It is crazy. Yeah.
Jeez.
So for the concentrations, again, this is not particularly difficult, especially if you've got notes. I can't imagine why this would be difficult if you have notes. I'll go through briefly what each of these is and explain one wrinkle that I think you really have to understand. But aside from that, it's not really that hard. We'll start off with mass percent. So in this case, we're looking at a solute and a solvent, So generally speaking, we have something in here. We have, this will be the solvent doing the dissolving, and then the solute up here. I can say a couple of things. I can see solute equals liquid or solid.
Oh, whoops. Solvent is aqueous.
Solvent is not necessarily aqueous. It could be anything.
Right.
But I will say this: a solvent can be liquid only. Only liquid, right? You can't dissolve something in a solid. It just doesn't work out very well. But a solute, though, can be a liquid or a solid. I mean, the thing is, you can add a liquid to a liquid, and it can dissolve. You could add a solid to a liquid, you can have it dissolve. I mean, we see examples of that all the time, right? I'll just give you a very, very easy example. Liquid chlorine, that would be considered a solute. A chlorine tablet is also considered a solute. But water then would be the solvent. Now, in order to do these kinds of calculations, one thing you have to be aware of course, is density is equal to mass divided by volume. And you need to be prepared for any and all kinds of commutations and permutations that involve liquid solutes, solid solutes, and liquid solvents, as well as the ability to interconvert between masses and volumes, or volumes and masses given a density. As long as you can do that, then you're fine. The thing is, though, if you don't practice enough of these problems, then you might not get a chance to look at all of those different combinations and permutations that I just mentioned. So be aware that you are going to have to be savvy about all of that. So it says here, given the mixture of the following two compounds, you've got 25.00 grams of X. Now understand that if it's grams of X, if you're given grams of something, that could be, X could be liquid or solid. If you've got mils of X, X can only be liquid. And I think that's important to realize as well. So for this specific one, we know what mass percent is, and the percent of X is going to equal grams of X divided by grams of X plus grams of Y. And you can see here that that's what we have, luckily, but we won't always have that. If you had mils of X would have to be converted into grams of X using the density formula, and volume would be equal to mass divided by density.
I have a question. Whenever you wrote down gram and then milliliter, the in between double X, what is that? Is that multiplication?
No. Mils of X can only be liters.
No,
it's not multiplication. What I'm saying is, if you're given grams of X could be, liquid, I should say. I meant liquid. X can be liquid or a solid if you're given X in grams, but if X is given in mils, it can only be a liquid. So that's just something to think about. So if you wanted the mass and you were given a volume, you'd have to use mass equals volume times density. If you wanted a volume and you were given a mass, and you'd say volume equals mass divided by density. So you have to be aware of how to interconvert between things. So for 17, understand that, when you do these, you could get a milliliters here, and you'd have to do that conversion. Now for 18, we're looking for molarity. Molarity is concentration. Molarity equals moles of X over volume of solution in liters. Now that's where the wrinkle comes into play here, because if you've got a volume of solution, and that's the key word there is solution. Solution is going to be all the combination of all liquid components. Okay, so it's all liquid components. And what's going to matter is that if X is solid,
excuse me,
solution equals volume of Y only. If X is liquid, solution equals volume of X plus the volume of Y. And that's important. That's important. So if you look at number 18, we've got a mixture here of two compounds. We've got 65.00 mils of X. You see the mils, that immediately should trigger you and say, oh, okay, that X must be a liquid. If X is a liquid, that means that the solvent, solution, sorry, would be X plus Y, which is going to be the X plus the Y value, whatever we get for the Y as far as the volume goes. We've already got actual volume of that 715.00. So a fair question would be for you, well, how are you going to know if you've got a solid or a liquid solute? If you, let's say you are given grams, how are you going to know? Well, I think what I've done here is if it is grams, one of two things happens. Either I didn't include a density, or I've actually said X is a solid. I have a feeling it's the former though. So if you're not given a density, then and you are given a gram value of X, then you can assume that it is a solid. In which case, you know, there's no way to calculate a volume for it.
You said if you give us the density or just tell us it's a solid, it'll be a solid, right?
No, if you don't get the density.
If you don't get the density?
That's right. If I don't give the density, you can assume it's a solid.
Okay. No, all right, solid, no density. All right.
All right, but if you get given the density, you can assume it's a liquid.
Right. But I mean, all right, I'm gonna be that guy, but you can, I mean, can't like objects be like solids be dense as well? Like,
Sure they can. Yeah, yes, but the point is that if you've got an Alka-Seltzer, think about this. Think about an Alka-Seltzer. How much does the Alka-Seltzer change the volume of the solution when you put it in? It's not really appreciable, is it?
Does it it absorbs the water, right?
Well, it dissolves into the solution.
Okay.
All right, but technically it doesn't really affect the volume of the solution very much. However, there are things like, I can't remember, there are certain antacids that are actually liquids that you put into water. And those would actually change the volume of the solution.
Right, right.
You're adding a liquid to a liquid. So that's the difference. That's the difference there, Adam.
Okay.
That's why we have this distinction here for molarity, because it's based on the volume of the solution, and the solution volume varies depending upon what components make up the solution. If it's a solid, you're only interested in the initial solvent volume. That's it. If X is a liquid, then the solution is going to be the combination of those two volumes.
Okay.
So in this instance, you can see that we are clearly given a volume of X, and we know that the total volume would be 65 plus 715. We don't have a choice here. And then we can also figure out the moles of X here. But you see, we're given the volume, which means we need a mass. How do we get the mass? Well, we use this over here. So we take if we're looking at 18 here, 65.00 mils would need to be converted into grams and then into moles.
Yeah.
And we do that using the density equation up the top. And then we've got don't forget you are given the molecular weight there as well to get the moles. So that's the main thing I want to focus on with molarity. Does anybody have any questions about that? The one after that is molality. Molality and molarity are two different animals. Molality I'll juxtapose them here so you can see.
Is that molality? That's kilograms over liters?
Close, but not quite. Molality, if I can spell it, there we go, is equal to moles of X. And this is important, kilograms of solvent. So for molality, it doesn't matter if X is a solid or a liquid, because we're only interested in the kilograms of solvent. So the nature of X here doesn't matter. It mattered for the molarity, because that was volume of solution. That's the key word there, solution. So just a reminder here. Solute, solvent. When you put them together,
The solution.
You get solution.
So it's like within the solution. Yep. All right. I just answered my own question in my head.
Okay, good. Good. So that's the difference there. And I think that's where people often fall into a trap, is they try and combine things for the molality they shouldn't. Whereas for the molarity, that's what it's all about. It is about just volume of solution. So it doesn't, the molarities are actually easier because you don't have to worry about what X is. Obviously, you still have to be able to convert it and get the moles of it, but that's not the hard part. The hard part is knowing what to do with it. So we're only interested in this 700.00 mils of Y, which would need to be somehow converted into kilograms. Now, the way we would do that, 0.00 mils of Y, we would convert that into grams of Y. How? We'd use the density calculation. So mass equals density times volume. That's how you do it. And then you would convert that into kilograms of Y.
Hold on. I gotta wake up for this question. Oh. All right.
Note that you are given the density there. You can see it, right? In the question.
Yeah.
Right. And then you convert that to grams of Y. Then that can be converted to kilograms of Y.
Yeah.
Okay. So of course, 1 kilogram is equal to 1,000 grams. That's the conversion factor. All right. Any questions? about molarity or molality there. Okay. The last one here is mole fraction. Mole fraction is not incredibly difficult. It's the Greek letter chi. It's not an X. It's chi. And if we're looking for the mole fraction of X, it'll be mole of X over mole of X plus mole of Y.
That Greek letter, is it like a squiggly diagonal backwards S?
Yes. Yeah.
And then cross? Yeah.
Yeah, that's right. Yeah. Actually, going back to the percent, one thing I did think I forgot is to add the times 100%. I can't really do that now, but for the mole fraction, it's a fraction, so we don't multiply it by 100%. I can tell you that. But the mass percent, I think I neglected to add the 100% on it, or multiply it by 100%. So just go back, in your mind, if you can, just go back and then make that correction for me. Anyway, we've got these. You got the volumes, and you got them, and we need to convert them into masses. And you'll notice for this one, we do already have a mass, so we don't have to convert that into a volume. And then we can calculate the mole fraction pretty easily from there. So any questions? Okay. Now for the colligative properties. Now the concentrations are all about the solute. Sorry. Yes, concentration is all about the solute. In general, it's always solute in solvent or solution. I mean, that's every single concentration ever. That's what it's all about. Solute in solvent or solution.
Is colligative properties, is that when osmosis comes in?
Yeah, that's right. Now, that's all about the solvent. So colligative properties are all about the solvent. And that sometimes creates a little bit of confusion as well. So concentration is about the solute and colligative properties are about the solvent.
What's about the solutes?
Concentration.
Concentration.
Mm-hmm.
So like, I'm about to Google it. Hold on. Relating to the binding together of molecules, colligative properties.
I think it's more correct to say, or a little bit more. I think it's better to say this. Colligative properties are properties that depend upon how much is dissolved and not what is dissolved. So I've in my videos, I give some examples of colligative properties.
That makes sense. Because it's like, I mean, it just makes sense just by looking at the formula.
Right, well, and what I've got here are the formulas for certain colligative properties here. And they're given to you, right? They're the ones that are right here. So we've got freezing point depression, which we did a lab on. We've got boiling point elevation here. We've got vapor pressure lowering, and then we've also got osmotic pressure, which is here.
Yeah. Osmotic pressure, that's molarity, R constant, and temperature.
That's right. Yeah, and I'll give you the value of the R constant at the bottom there as well. Do you see that? Temperature's in Kelvin, so.
Okay. The delta T's, That's molality, right?
No, the delta T is a freezing point depression and freezing point elevation. Oh, sorry, boiling point elevation.
Yeah. Okay.
All right, we did freezing point depression way back in that first lab. Do you remember?
Yeah.
The KF lab. Yeah. Now the link to, there is a link to concentrations, of course. So the osmotic pressure is related to molarity. The freezing point and boiling point changes are due to molality, and the, oh, that shouldn't be a C. I don't know why that came. Well, it
is a concentration.
Yeah, but it's the mole fraction. I might go in and try and change that. I don't know. Maybe it didn't accept my character that I put in there. I have to put in a different character, but it should be the mole fraction. I will try and change that. But yeah, it's the mole fraction is what that is. But again, you know, you'll have your notes there, so I don't really see that it's that big a problem. So looking at these, I'll very briefly go through what these colligative properties are. The first one we'll talk about is freezing point depression. If you've got, let's say you've got ice and you put something on top of the ice, what's going to happen is the ice is going to melt in order to try and dissolve the X that you put on top of it. That tends to depress the freezing point. So it lowers the freezing point of the ice. It's the same concept that's used when we put salt on icy roads. It actually lowers the freezing point.
Happened? What happened?
No, I don't know what happened. Adam, looks like you're frozen, buddy. Just like this ice here is. Whoops. Looks like it says my internet connection is unstable.
I'm hearing you fine.
Oh, okay. Thanks, Rebecca. All right. Looks like Adam had to, now there's two of him.
Oh my goodness.
I don't know if I like that.
Uh-oh.
There we go.
Oh, here he is. He's back. He's going to go one now. Two become one. All right.
All right.
We got our colligative properties. And we're talking about the ice here, having to melt that. The other thing we could talk about is if we've got a solution, we're going to have molecules of that solution above. So when we dissolve something in that solution, what happens is that the X that floats above it come back down to help dissolve what's in there. And that has two effects. It lowers the vapor pressure, but it also increases the boiling point, because the boiling point is all about getting the vapor pressure to, well, effectively the atmospheric pressure. So anything that's trying to reduce the vapor pressure requires a higher temperature in order to boil. So it does raise the boiling point. It's why people add salt to their pasta when they're cooking it. And the last one here is osmotic pressure. And what happens here is if you dissolve something on one side, then, oh, this is what's called a semi-permeable membrane here. Water can get through or solvent can get through, but the solute can't. What will happen is that the liquid in here, the pure liquid, will help try and come and try and dissolve what's in here, which will mean that there's a certain pressure that's being placed here, and that will, well, the pressure's on the piston here, I guess. So this is going to go up, and it's going to put a certain pressure on. That's osmotic pressure. I'll give you an example of that. I think a lot of people have done that experiment where you take a potato and you put it in salt water. Anyway, what happens is that the skin of the potato is a semi-permeable membrane, and the water in the potato actually goes into the salt water, and this potato shrinks. So that's osmosis right there.
Oh.
So
that's like literally osmosis is just An absorption of water.
Well, it's the movement of water through a semi-permeable membrane into a solution that has something dissolved in it. Like salt.
Like the solvent.
Yeah. Yeah. So that's osmotic pressure. And those formulas there are how we deal with it. So for something like number 21, your
Hold on. Is that how they make potato vodka?
no, that's a fermentation process. That's something different. That's something different. Very different.
Okay.
All right, 21. We're looking for boiling point here. So delta TB is equal to KBM. Now KB you're given. That's the mole boiling constant. So you don't have to figure that out. The M here is the molality. It's the molality of X in the solution. And that would be how you get the delta TB. But the new boiling point, which is what we're interested in, is going to be equal to the boiling point pure, which you are given. And it's important here, but you know it's going to be plus. It's going to be plus the delta TB.
Wait, that's boiling point, right?
Yeah, BP. But notice how here you are given the boiling point of the pure solvent. See that?
Yeah.
Yeah. And you're figuring out the delta TB based on the formula above.
Okay.
Now, number 22, this one is about freezing point. And that's going to be KFM. This is the mole freezing constant. This is still the molality of X. And it's a freezing point depression. So the new freezing point is going to be the freezing point pure minus the delta TF. So that's important to note as well.
Where do those last equations come in?
I'm sorry?
The new freezing point and new boiling point?
Well, if you look at
after multiplication, or
yeah, well, yeah, after you've done after you've figured out delta TF or delta TB, then you can apply that last one.
oh yeah, for sure. This one here, the vapor pressure lowering, the change in vapor pressure, we'll call it delta P, is equal to the chi of X, which is the mole fraction, multiplied by P naught of Y, which is the vapor pressure of the pure solution. It's pure solvent. This is going to be the mole fraction of X. So the new vapor pressure is going to be P naught
minus delta P. So you're actually using that P naught twice, but it's vapor pressure lowering, which is why it's minus. All right, does anybody have any questions about number 22?
That was 23.
Oh, 23, sorry.
Yep.
Okay. Number 24, that is osmotic pressure, MRT. M is molarity. This one's pretty easy, actually. Molarity of X. R is the R constant, which you're given.
Is there like two different R constants?
There are, but they have different units.
Yeah.
Yeah, one's joules per mole per Kelvin, and the other one's, this one, liters atmospheres per mole per Kelvin.
The other one is, it's, yep, I get it, 8.314.
Yeah.
Yeah.
But that's, I can't remember the unit, was it liters, kilopascals or something? Anyway, there's an 8.314. I can't remember the units go along with that because I've been using this one for so long.
Right.
All right. So that's it for the concentrations and the colligative properties. I'd still recommend, obviously, going through and looking at those videos.
Oh, yeah.
Otherwise, you know, you can end up getting mixed up pretty quick, no matter how good your notes are. All right. Let's take a look at some coordination chemistry. Now, again, you know, I guess it would be pretty easy not to deal with coordination chemistry at all and just to mechanically go through and just figure out the pattern of answering the questions and not really understand anything to do with coordination chemistry, which is unfortunate, but I don't know. I don't know how else to handle this stuff. But if you've got M, A, B, C, D in brackets and a BR2, the way that should be interpreted is like this. Now, I haven't included the stereochemistry here that goes along with it. But that's what that's how I know I could express it. The M in the middle is a metal, and then connected to it, we've got these different things called ligands or ligands, depending on where you're from. And everything in the brackets is what's connected, or the parentheses there, or square brackets, I guess, is connected to the M, and everything else is on the outside. So if I've got M, A, B, C, D, and I've got this situation of two BRs hanging around on the outside, then I know that that's what it looks like. And if it's BR negative, it means that everything inside those brackets must be a 2+ charge. So theoretically, if I know the charges of A, B, C, and D, then I can easily determine the charge on the metal. So if I know that everything adds up to 2+, then I know that M plus, in this case, -1 plus -1 plus 0 plus -1 equals +2, and I can solve for the charge on the metal. So that's all you're really being asked to do there.
Where does the third -1 come in?
The third -1, that's the charge of D.
Oh, okay. Wait, so where does the 0 come in then?
It doesn't. But you know, you can see now that you see what charge M would have, right?
Because there's two bromides, right?
Yeah, and they each have a -1 charge, right? because of where they are on the periodic table. They're in group 7, so they have a -1 charge. If the 2 bromines have a -1 charge, it means that everything in the square brackets must be +2.
Right. Well, those two bromides make the 2+.
Yeah, that's right. But the bromides themselves are -1 each, which makes that +2. Because this is a neutral compound, right?
So, hold on. I'm still kind of lost. Where does the 0 come in? Like, is that what M is?
No, the 0 is the charge on C.
Oh, I'm sorry. I was looking at 26. My bad.
We're looking at 25 here. All right, let me put 25.
Sorry.
That's all right. So are you okay with it now? All right, good. Now 26, it's a slightly different story, but you know, you got K's there. Now K, and again, don't worry about where these go, but they are all attached to the M. K is going to be 1 plus, 1 plus. That whole thing's going to be -2.
Mm-hmm.
And we can sort it out that way.
So, it'll make a +2 charge?
On the K's, yeah. And then a -2 on the brackets.
Right. I mean, like, if we're solving the charge for M.
Solving for it. Yeah, so it'd be M plus -1 plus -1 plus -1 equals -2.
2 minus.
Yeah, or -2. Right? Yeah, so that would mean, yeah, M would be -2 plus 4, which would be +2, right?
Yeah.
Yeah. Not that hard, is it? Nah.
Straightforward.
Yeah. A metal has an atomic number of 23, and its charge is +3. How many d electrons does the metal ion possess? Ooh.
Do you electrons as in like the electron configuration? Like,
yeah, that's right. So let's take a look at this one. We'll see where we go with it. So 23. Actually, you know what? The periodic table is useful for this one, so I'm glad I have it up here anyway. There he is. 23. That's vanadium, right? Oh, sorry, went too far. People tell me I always go too far.
hold on, I can pull up a periodic table on the browser.
It's all right. So vanadium. Whoops. Vanadium. So, you know, you can do it. You go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then it would be 3d3. All right, so that's...
Hold on, which one are we're looking at? Vanadium.
Vanadium.
Oh,
yeah.
because D is the transition metals, right?
All right. Now, you see, everything up to here, this is why we don't really need to worry about it. Oops. Wait, no, I did go too far there. Let's try this again. Rebecca, how are you doing?
I'm good, just following along.
Just following along, okay.
Yeah.
So for everything that we talk about, you can just sort of disregard it and just include that all as argon, and we're just worried about the 4s2 3d3 business.
So there would be 3.
Oh, no, not yet. Hang on. Wait for it. Right, now what we can say for all of these D elements here, that the number of Ds in this is neutral V, right? Neutral garden variety V. And that's important to note. There's no charge on it. Not neutral. Right, neutral, no charge, right? That's what it's going to be. For all these, it's going to be D whatever the second number is. So this would be D9, D8, D7, D6, D5, D4. So it makes it pretty easy. But that's for the neutral. But let's go back to the actual question here. The charge is +3. Oh, so we're looking at V3 plus, which means that it's V with 3 electrons.
So it'd be
Lost.
6d3, or would it add or would it lose? Oh, so it goes.
Well,
it goes back to 4s2. So that's the second. That's calcium, right? Yeah, that's calcium.
Oh, no, don't think about it like that.
Oh.
No,
Okay.
it would have the issue here is that when you're dealing with these coordination compounds, that once these things lose electrons because they're with ligands, then what happens is that the electrons that get lost are actually the first ones that get lost are the 4s2s. The 4s2s are the first to go. So what happens here is that V3 plus would be AR and 4s2s and 1 electron gone to be 3d2. So we lose the 4s2s plus 1d, one of the 3d.
Right. So what? I forgot. Why does it take the S again? Like,
Well,
is it because it's the most?
As it turns out, it's a higher energy of the two. It doesn't look like it is there, but it turns out that when it's in a complex, with things connected to it, the S is actually a little bit higher than the D. So the S's are taken first, and then any D's. So the answer to this question here, how many D electrons does the metal ion possess? It would actually be 2, because we end up with 3d2.
We were doing something like this at the end of Gen Chem 1. It had to do with the pairing of the electrons.
Right.
And filling each level, sub-level, I guess.
Right.
Is that what this is?
Sort of. Yeah, it's related to that, Rebecca.
Okay.
It's not entirely, but yeah, it's related to it.
Okay.
So what if it was what's the latter? Oh, all right. So what if it was reactant nonmetals with a positive?
No. We're only interested here in the D elements, Adam.
Yeah.
Just these puppies here. SC up to zinc. That's it. We're only but that's all we're interested in. These are the ones that will form these transition complexes.
Right.
And again, I can't stress enough the importance, I think, of watching those videos, because I think they really do help. Likewise, with the isomerism question, I think that it's helpful to watch the videos for that too. All right, let's. But I will go through the isomerism here, because that's kind of a difficult concept. So we talk about. Well, I go through in the video. I talk about 3 different kinds of isomerism, and those are anion exchange, I talk about geometric, and I also talk about stereo isomerism as well. Now, for some of these, there's 2 answers that would actually work. So just be aware of that, and that either answer would actually be okay. And you'll see that when you go through and you answer these questions, it's going to be obvious as to what's what. And again,
does that say stereoisomerism?
Stereoisomerism.
Isomerism. All right.
Mm.
Thank you.
So what I can tell you for sure is the following. Anion exchange needs something with a negative charge on outside. On something outside. So unless you've got that, then anion exchange is impossible. Technically also you need something with a negative charge inside as well for it to exchange with. But generally that's going to happen anyway. I can't imagine too many instances where that wouldn't happen. Since you don't know the charges on this A3 and B3, then you're kind of left without that information, but you can make the assumption that if there's, if you've got a K on the outside, for example, I can tell you this, anion exchange ain't going to be possible. Why? Because there's nothing negative on the outside. If you've got a BR on the outside, then anion exchange would be possible. But if you've got a K, there's no way that the K can exchange with anything inside because the K is not negative. I'll give you an example. Let's say it was M A3 B3 BR. Technically, if we knew that, say, A was negative, we could change it to MA2BR B3 and stick the A on the outside. That would work. That's what I mean by exchange. So that would be an example of that kind of isomerism. All right. Anybody got any questions? Now, geometric is a lot more subtle than that. Well, let's we'll skip over geometric, but we'll go on to stereoisomerism. Now, this is one. Okay, so the two times that we can get this to occur would be if we're dealing with a tetrahedral.
There's the geometry.
Right. It's tetrahedral, and we need 4 different ligands. And that's important.
Oh, man. That geometry was something else, man.
Yeah, but, looking at this, if I've got 4 different ligands, okay, I'll throw this at you. I'll throw this at you, Adam. If I've got 4 different ligands, how might that, just how might it be presented in a question?
It's like
no, look at this question here. See how it's got KMA3B3, right? You see that?
Yeah.
It's here, right? Yes?
Yeah.
How might it look if I had 4 different ligands? What would you see here? Can you guess?
Say the question again.
If I wanted to say that there were 4 different ligands, what would it look like?
I want to say MA4.
No. 4 different, sunshine. Different. A4 would be 4 of the same, wouldn't it? Yeah. How might I express 4 different ones?
Four different letters.
4 different letters. Yeah.
Thank you.
Look at
You're
that.
welcome. It was coming.
It was getting there. Look at that. Do you see that, Adam?
Yeah.
How much geometry do you have to know to figure that one out?
4.
None.
5. 5.
Anyway, there you go. Now, the M, you got the metal, and then you got 4 different things connected to it. So that would be an indication that you could do stereoisomerism, right? Now, look, I don't want to go into it here. I want you to watch the video, right? Watch the video, and it explains why we need 4 different ligands. The other thing is we can have, I'd say, 2 or more. Sorry, start again. I'm going to do that again. We could do an octahedral. Octahedral.
Oof.
And that's 6 different ligands. Oh, sorry, no, I wanted to say that.
That's 8.
No, I'm not. No, it's 6. 6
Wait,
ligands.
What?
Not different, not necessarily different though. 6 ligands. And we'll have, I'll say 2 or more. Well, let's just say En ligands taking up at least 2 slots.
My question is, octahedral? I thought, what's that prefix, man?
Yeah, it's based on, well, look what an octahedron is. Now, I'm not going to have to do this in 2 dimensions, which I don't like.
That's pretty good, though. That's good.
All right. An octahedron is 2 square pyramids joined at their base, right?
Yeah.
Yeah.
Well,
How many faces does it have? It has 8.
Yeah.
Right? It's got 8 faces. How many vertices has it got? 1, 2, 3, 4, 5, 6. All
Whoa.
right?
Oh. Whoa. Okay.
That's where it's octa because it's got 8 faces, but it's only got 6 vertices.
Huh. Okay.
All right. So if you've got an octahedral, which is going to look like that, really it's going to look like this. Okay, so that's an octahedral complex. But we can also have these ENs on there. Now, an EN is an ethylene diamine. And again, I don't want to go into this too much. But an EN will actually join 2 of those slots together.
EN?
Yeah, ethylene diamine. It's a bidentate ligand. It actually joins in two places, 2 adjacent places on the metal. But as long as you've got at least a couple of, I'd say, if you've got 2 ENs, then yeah, chances are you can end up getting 3. You've got 3. You can definitely have it. 2, you can most likely have it, and 1, you can sometimes have it. The stereoisomerism.
Is it like that's whenever both of them like contract, or?
No, it's an ethylene diamine. Looks like this.
Oh, it's a polyatomic ion.
No, it's not a polyatomic ion. It's got 2 It's got two ends that are capable of joining onto the metal.
Okay.
Right. So, you know, again, I'm really relying on people to watch the video here because, you know, I don't want to spend all this time.
Does it have the geometry on it?
The videos?
Yeah.
Absolutely, yeah. Right.
I'll definitely be watching it.
No, I think it's important.
Oh, yeah.
I'm just trying to give you some guidance here. So if you've got that kind of situation, then stereoisomerism is going to be possible there as well. The last one is called geometric. And I'd say this would be the last straw for you, really. I mean, if you can't do anion exchange, you can't do stereoisomerism.
So, all right, let me guess it. So geometric, there's like, there are so many, but I want to say there's like 2 to 7, like 2 to 7 different types of geometric.
No, not really, because we're only dealing with two geometries here, tetrahedral and octahedral. That's it.
Okay.
But if you've got no anion exchange, no stereoisomerism, then you can assume that geometric isomerism is possible.
Okay.
So if you had, an example would be this K2M A4B2. I know that that's, okay, Adam, I'm going to ask you this. How do I know that that's octahedral and not tetrahedral?
I mean, are we talking about just the concentration or K right next to it with it?
No, it's not concentration. It's what's in the square brackets is what's connected to the M.
I mean, it wouldn't be either one because there's 7.
No.
I would want to go with octahedral because there's 6 vertices.
There you go. Right. So
Yeah.
you look at the M and you look at what's with it. There's 6 things with it. If there were 4 things with it, it'd be tetrahedral, right?
Wait, so M is basically just in the middle and then
Yes. That's it.
Whoa, that's trippy.
Oh, yeah. It's mind blowing.
Yeah.
Now, anion exchange isn't possible here because there's no negatives on the outside. We've got Ks, they're positive. So no anion exchange there. And we don't have any ENs around. So we know that there's no stereoisomerism possible. So we must be dealing with geometric. And just a picture of what that would look like, there's 2 possibilities here. If we've got 6 things around it, we could do that, or, and I'll put these Ks on as well. The other possible way of handling it would be to do that. And if you look at the difference between those, you can see in the first one that the Bs are 180 degrees apart.
Mm-hmm.
And in the second one, the Bs are 90 degrees apart.
Hmm.
And that's different. That's an example of geometric isomerism. But but again, in summary, what I can say is look first for anion exchange, see if that's possible. If it is, great. Then look for stereoisomerism, see if that's possible. Look for 4 different things attached. Look for ENs in octahedral environments. And if that's not present, then you can assume it must be geometric. And this would be an example of geometric.
So for question 28, can we say it's geometric?
Yeah. That's what I would go with. Yeah. Because I know that anion exchange isn't possible. I know that stereochemistry isn't possible.
What was stereochemistry again? It was
four different things, right? Tetrahedral, 4 different things, or ENs in an octahedral environment.
Okay.
So either of those, and you can go for stereochemistry.
Okay.
Yeah. All right. Okay, last ones, and we're going to call it a day. Oh, we're almost at noon, but anyway, I'm going to keep cruising here. Okay, octahedral complex, strong field type. Oh gosh, all right. So again, I don't want to go into the niceties of this, and you really should watch the video. But in certain complexes, we get our D levels, which are 5 boxes that are all in a row. But in octahedral environments, they split. Excuse me, they split. And they split in certain ways, and I don't want to go into how they split. I do that in the video. But I'm just going to give you the quick and nasty thing here. Now, we've got 2 types of fields. We've got strong field. And strong field means that there's a large distance, delta. And the weak field, I'll tell you what, anybody who's not watching this is at a big disadvantage, I reckon. Anyway. So if you're watching this, congratulations, you're getting something easy here. And if you're not watching this, well, you missed out.
Nice.
So we've got a strong field, that's a big delta, big difference, and small is delta. If it's a big delta, then what you can is, it's like it has 2 different energy levels. And small delta, that's going to be like the same level.
Like the delta, I mean the change in what? Like going from the boxes from like D to like S or P or whatever?
Oh,
or?
no. The space between the boxes, the 2 layers. So you got the bottom and top. See that? Bottom, top, just the space between those 2, Adam.
Just by looking at the geometry of it, right?
Well, it's more about what's attached to it. Right, and you know, if you've got certain kinds of ligands attached, then it's going to be strong field. If you've got certain kinds of ligands attached, it's going to be weak field. Now, I don't have any questions about that, but that's the bottom line. So for something like this, if it says octahedral, then you know it's going to be 3 on the bottom, 2 on the top. If it's strong field, that's a big difference. And what that would mean is we put the 6 electrons in, they have to go in this way. They have to all go in the bottom. So it'd be 1, 2, 3, 4, 5, 6.
Okay.
Which would mean that there would be 0 unpaired electrons would be the answer for that. Now, had it been weak field, this is how it would have looked. It'd go 1, 2, 3, 4, 5, 6, which would leave us with 4 unpaired electrons. Because the difference there, the delta is so small that you may as well consider that they're all on the same line. We're obeying Hund's rule here, which means we put 1 in each before we start pairing them up.
Huh. It's like, I don't know how I see this. I'm looking at this, the 3 boxes like it's algebraically like bottom heavy.
Yeah, you can kind of look at it that way. But the thing is that you have to obey Hund's rule. Right? That means you put 1 electron in each and then you start filling the other boxes. But if it's a big delta, a big difference in energy here between the top and the bottom, it's like there's 2 different levels. If it's a small delta, but it's almost like they're on the same thing. And if they're on the same thing, that's how you'd fill them. You go 1, 1, 1, 1, 1, 1, and then 1 down here.
I'm gonna have to watch the video.
Probably, but that's
Yeah.
that's how you would do it. And
Right.
And a tetrahedral here, this one's a strong field type. Tetrahedral has 2 on the bottom, 3 on the top. Has 4 electrons, again, strong field, which means that I'd do 1, I do 1, 2, 3, 4, and that would be 0 unpaired electrons as well. If it was weak, field, it'd look like this: 1, 2, 3, 4. So it'd be strong, and that would be weak. But again, yeah, I'm expecting people are going to watch the video. I'm hoping they will.
So whenever it's strong, that's whenever it has the full amount of electrons in there.
Well, yeah, well, the strong, it's going to have certain ligands attached that are going to make the difference in energy here bigger.
From the bottom side, right? Or just...
Well, again, you have to watch the video. I don't want to, I can't. It's not,
I get it.
it's not a 30-second explanation that I can give you for that.
Yeah.
But I'm just giving you the quick and dirty here.
Yeah.
About what to expect. Rebecca.
Yes, I'm here.
Are you okay?
I am. I'm just taking notes and listening, and yeah, I feel pretty good about it.
Okay. Well, I don't really want to go into much more about this. I think we've done pretty much all we can.
Okay.
If anybody's watching this and they want, because I'm going to put this up obviously, and you want more help with this last part, then get a Zoom session going with me. But obviously, I don't think it's going to be that bad. I really don't. All right, so we'll leave it there for now, and I'll see some of you in about 8 minutes.
All right, sounds good. Thank you.
All right. See ya. I gotta go flip my chicken in the marinade.
Okay, go do it. All right, thanks everybody. I'll see you later.